In this module, we're going to consider motion of a system of particles and center of mass. We have often treated an object, be it a block, a car, whatever, as a particle. We can show that this makes rigorous sense as long as we choose the correct position in the object, that is, something we call the center of mass, to represent the entire object. Moreover, this approach doesn't just work for single extended objects, but also for any system of objects or particles. So recall that for a system, we have that the sum of the external forces is equal to the time rate of change of the total momentum of the system. And we can define this as being the total mass of the system times the acceleration of what we consider the center of mass of the system. We also define the total momentum of the system as the total mass of the system times the velocity of the center of mass of the system. But we also remember that the total momentum is given by the sum of the momenta of the individual particles in the system. That is the sum over the individual masses times their respective velocities. But this is also still equal to the total mass times the velocity of the center of mass. If we express the velocities as the rate of change of the positions of both the individual particles and the center of mass, then we can get a separate equation and we can rewrite this by pulling the time derivative outside of the whole thing, bringing the term on the right side to the left, and we get that the time derivative of the sum of the individual momenta minus the total momenta vanishes. This means that the term inside of the square brackets must be a constant. And in order for this equation to make sense for the case of a single particle where the sum is only over a single particle and that particle has the total mass of the system in it, and the position of that particle is the center of mass of that one particle system, then that constant must be zero. This gives us a clear and unique definition for the center of mass of a collection of particles. We can also write out a similar expression for an extended object. In this case, the total mass is going to be defined as the integral over every little bit of infinitesimal mass making up the entire extended object. Similarly, the sum over the individual particle's mass times its position will be replaced by an integral over the individual little bits of infinitesimal mass times their position. In summary, we can see that because the sum of the external forces acting on a collection of particles is equal to the total mass of the system times the acceleration of the center of mass of the system, and that this is equal to the time rate of change of the total momentum of the system, then the center of mass of a system behaves exactly like a single particle under the influence of the external forces. Forces internal to the system don't make any difference. The individual pieces of the system may move around due to these internal forces, but the motion of the center of mass is unaffected. If there are no external forces, the momentum of the center of mass is going to be constant. Let's consider again the example of perfect inelastic momentum exchange, but in this case, let's consider finding the center of mass of this system. That center of mass, of course, is given by the sum over the individual masses times their position, which is going to be equal to the total mass times the position of the center of mass. Let's let the mass 1 and mass 3 initially be at a position of 5 meters in our given coordinate system. And mass 2 is going to be at a position of 7 meters in our coordinate system. From our previous look at this example, we know that after the ball is thrown, mass 1 is going to recoil with a velocity of v1 equal to 2 meters per second. While the ball is in the air, it's going to travel with a speed of 20 meters per second. And after m2 catches the ball m3, the pair are going to be traveling to the right with a speed of 1 1/3 meters per second. But for now, let's consider the center of mass. To get this, we're going to take the two masses which are at position x1, 0, that is mass 1 plus mass 3, that total mass times their position. We're going to add to this mass 2 times its initial position, and that's going to be equal to the total mass, which is the sum of all three masses times the position of the center of mass. Now notice we're only doing the position of the center of mass in the x direction, There is a y center of mass, but because we're throwing a ball across and there is gravity acting, the center of mass in this case is actually going to be moving. Let's keep this simple for now and only consider the x center of mass. If we plug in numbers, we find that the center of mass in the x direction is 6.12 meters. All right, so this is a simple calculation for the center of mass of this system while it's all sitting still. However, we can go a little bit further in this example because while the masses m1 and m3 are in motion, there is a simple expression for the position of each mass. Because they're moving with constant speed, we know that the position for x1, we'll call this x1 tilde, is the initial position minus the velocity times time. And the position of x3, we'll call this x3 tilde, is again the initial position plus the velocity of the ball as a function of time. And going back to our previous working of the problem, we can replace v3 by its expression in terms of the recoil velocity v1. And we now have expressions for the positions of the mass m1 and the mass m3. Of course, mass m2 is just sitting still because it hasn't caught the ball yet, so it's still remaining in place. We can now calculate the center of mass of the system by taking mass 1 and multiplying it by its position as a function of time, plus mass 3 times its position as a function of time, plus mass 2 times its constant position. This will be the total mass of the system times the center of mass as a function of time. If we replace x1 tilde and x3 tilde by their equations in terms of time, we notice that the terms involving time cancel each other out. The result is just that we have m1 times the initial x position for particle 1, m3 times its initial position, plus m2 times its initial position, which is equal to total mass times the position of the center of mass as a function of time. But time has dropped out. And if we look carefully, we see that what we have is that the time-dependent center of mass, while the ball is in the air, is still exactly the same as it was before we threw the ball at 6.12 meters with no time dependence. Now, after a certain amount of time has passed, the ball is going to reach the person with mass m2. That amount of time, let's call it t tilde, can be determined by saying that t tilde is the time at which the position of the ball, x3 of t tilde, is equal to the initial position of the person at x2 naught. So solving this for t tilde, we get an expression that we can use to express the position of the person catching the ball for times after the ball has been caught. After catching the ball, the person and the ball will move with a constant velocity, and their position, x2 as a function of time, can be easily expressed as their initial position plus their recoil velocity v2 times now the quantity t minus t tilde. We need to include this offset t tilde so that when t equals t tilde, the position x2 as a function of time is equal to the initial position. Eliminating the term t tilde in terms of its expression, we get a somewhat more complicated expression for x2 as a function of time. But we can still use this in the equation for the center of mass of the system now. Now that center of mass is going to be given by m1 times x1 tilde as a function of time. The person of mass 1 is still moving with the same constant velocity that they were after initially throwing the ball. But now the second part of the system is the total of masses m2 and m3 together at position x2 as a function of time. But this will be equal to the total mass of the system times the center of mass of the system as a function of time. Expanding x1 tilde and x2 as functions of time, we see that, again, certain terms cancel. The time-dependent terms cancel each other, and there is also a pair of terms involving mass 3 and x2 naught, which cancel. And together, what we find in the end is that we have the exact same center of mass as we had before throwing the ball, and that is that the center of mass as a function of time is simply at 6.12 meters. Because there are no external forces acting on the system, the center of mass of the system behaves as it would under the influence of all the external forces. There are no external forces. there was no initial momentum. So the center of mass of the system is simply going to remain in place as it was before, with the center of mass at 6.12 meters.